In mathematics, the pigeonhole principle states that if n items are put into m containers with n greater than m, then at least one container must contain more than one item. This theorem is exemplified in real life by truisms like, there must be at least 2 left gloves or 2 right gloves in a group of 3 gloves. It is an example of a counting argument, and despite seeming intuitive, it can be used to demonstrate possibly unexpected results. For example, that 2 people in London have the same number of hairs on their heads. The first formalization of the idea is believed to have been made by Peter Gustav Lejeune Dirichlet in 1834 under the name Shubfach Principle. For this reason it is also commonly called Dirichlet's box principle, Dirichlet's drawer principle, or simply Dirichlet's principle, a name that could also refer to the minimum principle for harmonic functions. The original drawer name is still in use in French, Polish, Bulgarian, Turkish, Hungarian, Italian, German, Danish, Chinese, and Japanese. The principle has several generalizations and can be stated in various ways. In a more quantified version, for natural numbers k and m, if n equals km plus 1 objects are distributed among m sets, then the pigeonhole principle asserts that at least one of the sets will contain at least k plus 1 objects. For arbitrary n and m, this generalizes to k plus 1 equals per meter plus 1, where is the floor function. To do so requires the formal statement of the pigeonhole principle, which is, there does not exist an injective function whose codomain is smaller than its domain. Advanced mathematical proofs like Siegel's lemma build upon this more general concept. Examples: sock picking. Assume you have a mixture of black socks and blue socks. What is the minimum number of socks needed before a pair of the same color can be guaranteed? Using the pigeonhole principle, to have at least one pair of the same color using one pigeonhole per color, you need only 3 socks. Handshaking. If there are n people who can shake hands with one another, the pigeonhole principle shows that there is always a pair of people who will shake hands with the same number of people, as the holes, or m, correspond to number of hands shaken, and each person can shake hands with anybody from 0 to n-1 other people. This creates n-1 possible holes. This is because either the 0 or the n-1 hole must be empty. This leaves n people to be placed in at most n-1 non-empty holes, guaranteeing duplication. Hair counting. We can demonstrate there must be at least 2 people in London with the same number of hairs on their heads as follows. Since a typical human head has an average of around 150,000 hairs, it is reasonable to assume that no one has more than 1 million hairs on their head. There are more than 1 million people in London. Assigning a pigeonhole to each number of hairs on a person's head, and assign people to pigeonholes according to the number of hairs on their head. There must be at least 2 people assigned to the same pigeonhole by the 1 million and first assignment. For the average case with the constraint, fewest overlaps, there will be at most 1 person assigned to every pigeonhole, and the 150,000th first person assigned to the same pigeonhole as someone else. In the absence of this constraint, there may be empty pigeonholes because the collision happens before we get to the 150,000th first person. The principle just proves the existence of an overlap. It says nothing of the number of overlaps. The birthday problem. The birthday problem asks, for a set of n randomly chosen people, what is the probability that some pair of them will have the same birthday? By the pigeonhole principle, if there are 367 people in the room, we know that there is at least one pair who share the same birthday. As there are only 366 possible birthdays to choose from, the birthday paradox refers to the result that even if the group is as small as 23 individuals, there will still be a pair of people with the same birthday with a 50% probability. While at first glance this may seem surprising, it intuitively makes sense when considering that a comparison will actually be made between every possible pair of people rather than fixing one individual and comparing them solely to the rest of the group. Softball team: imagine 7 people who want to play softball, with a limitation of only 4 softball teams to choose from. The Pigeonhole Principle tells us that they cannot all play for different teams. At least 2 must play on the same team. Subset sum: any subset of size 6 from the set S equals 1, 2, 3, 9 must contain 2 elements whose sum is 10. The pigeonholes will be labeled by the 2-element subsets 1, 9, 2, 8, 3, 7, 4, 6, and the singleton 5 pigeonholes in all. When the 6 pigeons are placed into these pigeonholes, each pigeon going into the pigeonhole that has it contained in its label, at least one of pigeonholes labeled with a 2-element subset will have 2 pigeons in it. Uses and applications. The pigeonhole principle arises in computer science. For example, collisions are inevitable in a hash table because the number of possible keys exceeds the number of indices in the array. A hashing algorithm, no matter how clever, cannot avoid these collisions. The principle can be used to prove that in any lossless compression algorithm, provided it makes some inputs smaller, will also make some other inputs larger. Otherwise, the set of all input sequences up to a given length L could be mapped to the smaller set of all sequences of length less than L without collisions, a possibility which the pigeonhole principle excludes. A notable problem in mathematical analysis is, for a fixed irrational number E, to show that the set n is an integer of fractional parts is dense in 0, 1. One finds that it is not easy to explicitly find integers n, m such that n less than e, where e greater than 0 is a small positive number and a is some arbitrary irrational number. But if one takes m such that 1, m less than e, by the pigeonhole principle there must be n1, n2, 1, 2, m plus 1, such that n1a and n2a are in the same integer subdivision of size 1, m. In particular, we can find n1, n2 such that n1a is in m, and n2a is in m, for some p, q integers and k in 0, 1, m-1. We can then easily verify that a is in. This implies that n less than 1, m less than e, where n equals n2 minus n1 or n equals n1 minus n2. This shows that 0 is a limit point of n. We can then use this fact to prove the case for p in m, and by setting k equals sup Rn, r n less than j, m, one obtains n minus p less than 1, m less than e. Alternate formulations. The following are alternate formulations of the pigeonhole principle. If n objects are distributed over m places, and if n greater than m, then some place receives at least 2 objects. If n objects are distributed over n places in such a way that no place receives more than 1 object, then each place receives exactly 1 object. If n objects are distributed over m places, and if n less than m, then some place receives no object. If n objects are distributed over n places in such a way that no place receives no object, then each place receives exactly 1 object. Strong form. Let q1, q2, qn be positive integers. If objects are distributed into n boxes, then either the first box contains at least q1 objects, or the second box contains at least q2 objects, or the nth box contains at least qn objects. The simple form is obtained from this by taking q1 equals q2 equals qn equals 2, which gives n plus 1 objects. Taking q1 equals q2 equals qn equals r gives the more quantified version of the principle, namely, let n and r be positive integers. If n plus 1 objects are distributed into n boxes, then at least one of the boxes contains r or more of the objects. This can also be stated as, if k discrete objects are to be allocated to n containers, then at least one container must hold at least objects, where is the ceiling function, denoting the smallest integer larger than or equal to x. Similarly, at least one container must hold no more than objects, where is the floor function, denoting the largest integer smaller than or equal to x. Generalizations of the pigeonhole principle. A probabilistic generalization of the pigeonhole principle states that if n pigeons are randomly put into m pigeonholes with uniform probability 1 per meter, then at least one pigeonhole will hold more than one pigeon with probability where n is the falling factorial m. For n equals 0 and for n equals 1, that probability is 0. In other words, if there is just one pigeon, there cannot be a conflict. For n greater than m it is 1, in which case it coincides with the ordinary pigeonhole principle. But even if the number of pigeons does not exceed the number of pigeonholes, due to the random nature of the assignment of pigeons to pigeonholes, there is often a substantial chance that clashes will occur. For example, if 2 pigeons are randomly assigned to 4 pigeonholes, there is a 25% chance that at least one pigeonhole will hold more than one pigeon. For 5 pigeons and 10 holes, that probability is 69.76%, and for 10 pigeons and 20 holes it is about 93.45%. If the number of holes stays fixed, there is always a greater probability of a pair when you add more pigeons. This problem is treated at much greater length in the birthday paradox. A further probabilistic generalization is that when a real-valued random variable x has a finite mean e, then the probability is non-zero that x is greater than or equal to e, and similarly the probability is non-zero that x is less than or equal to e. To see that this implies the standard pigeonhole principle, take any fixed arrangement of n pigeons into m holes and let x be the number of pigeons in a hole chosen uniformly at random. The mean of x is n per meter, so if there are more pigeons than holes the mean is greater than 1. Therefore, x is sometimes at least 2 infinite sets. The pigeonhole principle can be extended to infinite sets by phrasing it in terms of cardinal numbers. If the cardinality of set A is greater than the cardinality of set B, then there is no injection from A to B. However, in this form the principle is tautological, since the meaning of the statement that the cardinality of set A is greater than the cardinality of set B is exactly that there is no injective map from A to B. However, adding at least one element to a finite set is sufficient to ensure that the cardinality increases. Another way to phrase the pigeonhole principle for finite sets is similar to the principle that finite sets are Dedekind finite. Let A and B be finite sets. If there is a surjection from A to B that is not injective, then no surjection from A to B is injective. In fact, no function of any kind from A to B is injective. This is not true for infinite sets. Consider the function on the natural numbers that sends 1 and 2 to 1, 3 and 4 to 2, 5 and 6 to 3, and so on. There is a similar principle for infinite sets. If uncountably many pigeons are stuffed into countably many pigeonholes, there will exist at least one pigeonhole having uncountably many pigeons stuffed into it. This principle is not a generalization of the pigeonhole principle for finite sets, however. It is in general false for finite sets. In technical terms it says that if A and B are finite sets such that any surjective function from A to B is not injective, then there exists an element of B of B such that there exists a bijection between the preimage of B and A. This is a quite different statement, and is absurd for large finite cardinalities.